This is the weekly recap of MLF course, Machine Learning Foundations. Let's start with week 1. Week 1, we saw what a machine learning is. Machine learning, let's say a learning algorithm takes instructions from a human and also takes example data. It designs its own tool and creates a tool which takes the input, which could be a training data, and gives an output, which could be one real number in case of a regression problem, which predicts, or it could be like +1 or -1, a classification result. So that is what machine learning is. And one important point is we use machine learning not just because we want to, but when the human efficiency, scalability, and speed fails, and also a software application cannot solve the problem, and it also fails at all these three things, we use machine learning. A classic example is spam detection engine. So human cannot look out each and every mail and determine if it is spam or not. It's just not scalable, and everything else. And software application, when designed, the spammers have seen the patterns of this software engineer and had a work around it. So it failed. Hence, machine learning application was employed. So what it did was, it took a lot of examples of spam and not spam data, and it solved the problem. So that is how machine learning is used. Now, what is data? Data for a computer is just collection of vectors. As long as they are consistent, it's just collection of vectors, and it doesn't need any heading. But for humans to understand, you need heading, which is height, weight, age, and so on. These are called metadata. Metadata is also useful for storytelling. Now, what is a model? Model, remember a mnemonic MER. So what it is mathematical equation of reality. So PV is equal to NRT is one such model which gives useful, approximate but reasonable information. Okay. So, and what about learning algorithm? Learning algorithm, as I told you, takes the training data and gives a model. That is simply an equation, mathematical equation of reality. And then we'll see what the notation for rows and columns is. If X subscript of J superscript of I represents the subscript represents jth element of ith vector, and or simply to put it, J represents the features of the ith row, superscript represents the ith row. So if I say Xij, X subscript J and superscript I, and 1 less than or equal to I less than or equal to 569, 1 less than or equal to J less than or equal to 30, that means there are 569 rows of data with 30 features. Now let's go to the framework, regression framework. So that for the regression framework, the input is, the training data is in the form of x1, y1, x2, y2, so on up to xn, yn. Okay, this could be like 3, 9, 1.9, 5.0. So 3, 9, 1.9 is a vector, and the y value which is labeled is always a real number. So this could be thing, and then the function could be of the form 2 times rooms minus 0.5 into distance, or G could be another model which could be rooms plus 2 times of distance. So this could be the model. So F goes from RD to R, and G goes from RD to R, let's say. And loss is 1 by n times f of xi minus xi whole square. Now, so to generalize this equation F, we can write it as F transpose X plus P. Okay, and it could be any of the model. And out of so many models, it picks the best model which has least loss. And the output of regression is continuous in general. It could be discrete and also infinite in range, because the output is R, which goes from -infinity to +infinity. Classification, the input is same as that of regression framework, and the F goes from RD to +1 or -1. The last loss is sine of this function. So sine of, let's say, area minus 10 is a model, or price minus 6 is your model, whatever that sign. And if wherever it is not equal, that is by the total, is your loss. Or for more than 2 classes, okay, then you can use the same loss function for the regression as this one. So output in general is discrete and finite in range, that is -1, +1. Then we have to see what is a validation data, training data, and testing data. So let's say 80-20 split. This is one standard way where you see entire data can be divided into 80% of it as the training data, 20% of it as testing data. Out of the 80% of the training data, you pick out the 20% and you call it as validation data. So there are, for a learning algorithm, it has infinite possible models, but out of which it has to pick the best one model. Let's say it picks 3 or 4 models which it thinks are of least loss. Now it goes to validation data and tests these models on that validation data and picks one. So that's how validation data is useful for hyper tuning of the model. Now let's see what dimensional reduction is. So we have seen regression, we have seen classification. These falls under supervised learning. Dimensional reduction and density estimation falls under unsupervised learning. So for dimensional reduction and density estimation, the data is the input is in the form of x1, x2, x3, so on up to xn. And for dimensional reduction, there is an encoder function f goes from rd to rt dash, where d dash is less than d, the dimension. And decoder function g goes from rd dash to rd. So the goal of it is g of f of xi is approximately equal to xi. So the function could be like x1 minus x2 or x1 plus x2 by 2, and g of u could be u comma u, and you see which functions, which models has the least loss, and it picks that function. The loss is 1 by n sigma I running from 1 to n, norm of g of f of xi minus xi whole square. So density estimation, we know what the input is, then the output of the density estimation is a functional, is a probabilistic model. So P goes from RD to R plus, and the loss is 1 by n sigma I running from 1 to n minus natural logarithm of P of xi. So let's conclude this week 1 with simple question. Like after training data, model 1 got 90% efficiency result, okay, and model 2 got 61%. But after test data, model 1 gave you 85% and model 2 gave you 60%. Which model do you prefer, M1 or M2? 90 to 85, there is 5% difference, and 61 to 60, obviously model 2. Now going to week 2 is all about representations. First is closed and open ball. What is a closed ball and what is an open ball? B, or with the center and an epsilon radius, can be represented or stated as an open ball or a closed ball, and it is represented as b of x comma e is y belongs to rd, d of x comma y is less than epsilon for all x belongs to rd. So if y belongs to rd, d of x comma y is less than or equal to epsilon for all x belongs to rd, then we call it as a closed ball. Now what is d of x comma y? D of x comma y is norm of x minus y, which is square root of x minus y, x1 minus y1 whole square plus x2 minus y2 whole square, so on up to xn minus yn whole square, where x1 is a vector going from x1 to xn, y is a vector going from y1 to yn. Now another point is the dot product. So dTP is what a mnemonic is to remember. Dot product can be represented in 3 ways: x dot y, x transpose y, or sigma I running from 1 to n xi times yi. So this is what it is. And then you have what is differentiable at a point. So if a function f of x is differentiable at a point x star, when is it differentiable? When limit x tends to x star, f of x minus f of x star by x minus x star is equal to f dash of x star. So this f is differentiable at x star, that means it is continuous at x star. If it is not differentiable, it is not continuous at all. Then comes the linear approximation, quadratic approximation, and cubic approximation. So general form of the equation is f of x is equal to f of v plus del of f of v transpose into x minus v. So linear approximation formula is y is equal to f of a plus f dash of a into x minus a. Quadratic, y is equal to f of a plus f dash of a into x minus a plus 1 by 2 factorial into f dash of a into x minus a whole square. Cubic is y is equal to f of a plus f dash a into x minus a plus f dash a by 2 factorial into x minus a whole square plus f triple dash of a by 3 factorial into x minus a whole cube. So you can simply correlate this with Maclaurin series. So for Maclaurin series says that if f of x is your function, then expansion of f of x is f of 0 plus f dash of 0 into x plus f dash of 0 into x square by 2 factorial plus f triple dash of 0 into x cube by 3 factorial, and so on. So you can simply like correlate and remember. Then what is a line passing through u along v, u which belongs to rd along v? Then x belongs to r du, x is equal to u plus alpha v, where alpha belongs to r. How about a line passing through u and u dash? There can be two possibilities. X belongs to r, x is equal to u plus alpha times u minus u dash, where alpha belongs to r, or x is equal to u plus alpha into u dash minus u, where alpha belongs to r. Now there is a hyperplane normal to a vector x with a value, let's say b. Then how do you represent this? X belongs to rd, w transpose x is equal to b. Let's say you want an equation of hyperplane which is normal to a vector 1, 1, 1 and whose value is 1. So w transpose x is like dot product between 1, 1, 1 and let's say x1, x2, x3. So it becomes x1 plus x2 plus x3 and whose value is 1, right? W transpose x is x1 plus x2 plus x3 is equal to 1. Now let's see what a gradient is. Gradient is like simply a package of partial derivatives in all directions. Del f of v is dou f by dou v whole transpose. So del gradient, if you see at a point, is perpendicular. So it is perpendicular. For example, gradient of f of v is perpendicular when f of x is equal to f of v, and also it is perpendicular to the linear approximation, that is your tangent at that point. And if you take this gradient del f of v, transpose it, del f of v, not transpose it, and do a dot product with the unit vector, then you get directional vector in that direction. So the directional derivative, sorry, not vector, directional derivative at a point v along a direction u of a function f is represented by d f of v of subscript u, and you get direction derivative. Directional derivative is an important tool. From a given position, which direction to move is determined by this direction derivative. So if you want to move in a direction to increase your function, or you want to move in a direction to decrease your function, to maximize, choose the direction which increases the function, to minimize, choose the direction which decreases the function. So decreasing of the function is called as descent, and increasing is called ascent. So finally, Cauchy-Schwarz inequality is minus norm A, norm B less than or equal to A transpose B, norm A less than or equal to norm A, norm B. If A is equal to alpha B or B is equal to alpha and alpha is greater than 0, A transpose A B becomes an equality and is equal to norm A into norm B. If A is equal to alpha B and or B is equal to alpha and alpha is less than 0, then minus norm of A, norm of B is equal to A transpose B. So that is inequality attains equality at these two conditions. Let's move to week 3, which is subspaces. So A is a matrix, M by N matrix. M is number of rows, N is number of columns. So M could be your dimension. N also represents a number of vectors. So it's considered that there are 3 features and 100 columns of data. 3 features and 100 columns of data. So here M is your 3 and N is equal to 100. All the set of vectors. Okay, so that is what A is. So let's say if A is a matrix with M rows and N columns. So M is a rows and N is columns. And we have row subspace, null space. I'm simply saying space instead of subspace. Row space, null space, column space, left null space. Now row space is represented by R of A for a matrix. Column space is represented by C of A for a matrix. Null space is represented by N of A of a matrix. And left null space is represented by N of A transpose. Now column of A is subset of Rm, and row of A, which can also be written as column of A transpose, is subset of Rn, and column of A as well as the left null space are subset of Rm. Row of A and null space of N of A are subset of Rn, which are N is a column. Now what is column matrix? See, Ax is equal to B is your, column space is Ax is equal to B, null space is Ax is equal to 0, row space is all of A transpose T, and left null space is set of all Y orthogonal to column space. So now row space and null space are orthogonal subspaces. Column space and left null space are orthogonal subspaces. What does that mean? It is all the set of vectors in row space and all set of vectors in null space are orthogonal to each other. If you do dot product, it becomes 0. So how do you find column space of A, row space of A, null space of A given a matrix? Given a matrix, how do you find it? So this is step 1. Convert this matrix into reduced row echelon form. And then from there, if you see number of non-zero rows, these become the basis vectors of your row space, and span of these are your row space. Or for the column space computation, same, convert the matrix into reduced row echelon form, and then see the number of pivots. All the columns which have pivots in your original matrix A, span of those form the basis vectors, and the span of them becomes your column space. Now row rank of A is number of basis vectors, and column rank of A is number of its basis vectors, and row rank and column rank are always equal and is equal to rank of A. And if you see, there are non-pivot elements where there are no pivots. So such non-pivot elements are called as free variables. So these is also called as nullity. So rank of a matrix plus nullity of matrix gives number of columns. Now coming to the dimension of column space is equal to dimension of row space is equal to rank of A. Let's say it is R and is equal to 2. Then the dimension of null space is equal to n minus R, and dimension of left null space is m minus R. Now how do you compute null space of A? So reduce a matrix A into reduced row echelon form, identify the number of pivot columns and number of non-pivot columns. The number of parameters is the number of non-pivot columns. Let's say there are 3 parameters which does not have a pivot columns. So R, S, T be the parameters. Now express this matrix, express the matrix in terms of R of something plus S of something plus T of something. That way these somethings U1, let's say U1, U2, U3 form the basis, and these are the base span of this is your null space. Now what is the orthogonality? X dot Y is 0, or set of matrix, let's say, are orthogonal, then we call them as linearly independent. So if let's say V1, V2 so on up to Vk are mutually exclusive or linearly independent, we say CV1 plus C2 V2 plus so on up to Ck Vk is equal to 0. This is one other form of expressing it. What is orthonormal vectors? Vectors which are orthogonal also individually all the vectors are unit vectors. So U transpose V is 0 and norm of U and is equal to norm of V is equal to 1. An important observation is if Ax is equal to 0, this is the case of null space. Let's say you have row 1. If you see the matrix with rows, row 1, row 2, so on up to row m, and x1, x2, x3 matrix, which is n by n matrix. So m by n into n by n1 matrix, which is equal to 0, 0, 0. Row 1 is orthogonal to x1, row 2 is orthogonal perpendicular to x2, and so on. That means like c1 times of row 1 plus c2 times of row 2 plus c2 times of row 3 is perpendicular to x. So here you can clearly see that the row space is perpendicular to the normal space of A. Now projection, let's talk about projection. To project any matrix B onto A, simply left multiply the matrix B, to project any vector B onto a vector A, left multiply the vector B with projection matrix P. So P times of B is your answer, where P is A transpose by A transpose into A. So P is always symmetric, and P square is equal to P square into B is equal to P into B. So column space of a projection matrix is a line passing through A. So P, you are trying to project B onto A, right? So column space of a projection matrix P is a line passing through A. called null space of projection matrix is a plane passing through A. Okay, fine. Now, so how do you find the best fit line? So in order to find the best fit line, you can use a simple formula of theta is equal to A transpose A into A transpose A whole inverse into A transpose into B. So if AX is equal to B is the set of solutions, sorry, not solutions, but a set of equations when you are trying to find the best fit line. Theta is equal to A transpose A whole inverse into A transpose B is the formula. Now, when do you say that it is a full rank matrix? Full rank matrix has no zero rows, therefore matrix is invertible. Full rank matrix is a matrix where the columns of the matrix are linearly independent. Full rank matrix is a system of solutions which does not have infinite solutions. And for a square matrix, if determinant is not equal to 0, the column vectors are linearly independent. These are some of the properties that I am trying to tell you. So if A is called as a full rank matrix and n is less than m, then rank of A is n. Okay, if A of 5 by 7 is said to be a full rank matrix, then the rank of A is simply 5. Lesser than of 5 and 7 is what? Is your rank. So in RREF, reduced row echelon form, sometimes you get like in an augmented form you get all zeros, and on the right the y values you get some number 3. This implies it's an absurd way. It says like 0x1 plus 0x2 plus 0x3 is equal to 3, so there is no solution. And sometimes you get 0 0 0 and as well as 0 augmented matrix also 0. So in that case also it is infinitely many solutions. And some properties of determinant is like square matrix A is invertible if determinant is not equal to 0, and therefore also the column vectors are linearly independent. One is that. And determinant of P inverse AP is equal to determinant of A. And if in a vector, in a matrix, if one column is n times another column, then the determinant is 0. And finally, for a square matrix, the characteristic equation becomes the matrix itself. That is, let's say lambda square minus 3 lambda plus 1 is equal to 0 is a characteristic equation, which is nothing but lambda determinant of lambda minus ai. A minus lambda I equal to 0. That is a characteristic equation, and it becomes like a square minus 3a plus I is equal to 0. A square is equal to 3a minus I. So that is always there. Now coming to week 4, we can see that week 4 starts with linear regression, polynomial regression problems, and what is the loss function? Half times of a theta minus y transpose a theta minus y is your loss function, and if you minimize it, you end up getting theta is equal to a transpose a whole inverse a transpose y, which I have told you before. So first and foremost step to computing a best fit line is to check which kind of model you want to do. Based on the model, you write the equation or the matrix form like a, x and y in that form. Okay, so for example, if you want a quadratic, y is equal to theta naught plus theta 1x plus theta 2x square, then you simply write 1 1 1 1 x1 x2 x3 x4 x1 square x2 square x3 square x4 square theta 1 theta 2 theta 3, then y1 y2 y3. That fetches whatever the model you got. Now after getting this, you do an augmented matrix and see if it is solvable or not. If you get any of the rows equal in the augmented form, all the left side, not the y, all of these are equal, then it is equal to 0, then it is not solvable. Then you can use the formula A transpose A whole inverse A transpose y. If it is solvable, you can simply say theta is A inverse of y. And another observation is that the minimization of loss is same as maximization of the likelihood for a linear model, mind you. And there is something called as a regularization parameter. So theta regularization parameter is A transpose A plus lambda I whole inverse of A transpose Y. So instead of A transpose A whole inverse A transpose Y, you are adding plus lambda I, and lambda is called as regularization parameter. If it is too high, we say it as overfitting. If it is too low, we call it as underfitting. Now let's talk about set of all vectors said to be eigenvectors. All the set of vectors when multiplied with a matrix A, let's say, so AXI, and the result will be a vector which is parallel to X. You're simply creating another vector which either is shrinking or expanding, which is parallel. So which means that AX would stretch X, or so the direction remains unchanged, or it will shrink. All such special vectors or set of vectors x1, x2, so on up to x, and all such that AX is parallel to X are called as eigenvectors. Now if you see the projection, you're projecting B to A, PB becomes, the direction of PB changes and it will be along A. So PB is not a eigenvector, or B is not eigenvector, right? So that is one difference. Now trace is nothing but, so you have got let's say what do you call AX, right? We talked about AX. AX is equal to lambda times X. Okay, either it shrinks or expands, and it is parallel. AX is called lambda times X, and X is lambda is called as eigenvalue and X is called as eigenvector. Now for a given matrix, if you take the diagonal elements and add it, sum of the diagonal elements is nothing but, it is called as trace and is equal to the sum of eigenvalues of that matrix. And if you take a matrix, find the determinant, this is same as the product of the eigenvalues of that matrix. So for an n by n square matrix, n eigenvalues are present, and eigenvectors corresponding to different eigenvalues are always linearly independent, but eigenvectors corresponding to one eigenvalue may or may not be independent. Now let's say if A is a matrix and A plus 3i and A plus 100i are two different translations of this matrix. Eigenvalues of A is lambda 1, lambda 2, then eigenvalues of A plus 3i would be lambda 1 plus 3 and lambda 2 plus 3. And eigenvalue for A plus 100i would be lambda 1 plus 100 and lambda 2 plus 100. But the eigenvectors of A plus 3i, A plus 100i would be same, x1, x2. Now, so another observation is if a matrix is A is a symmetric or close to symmetric, then the eigenvalues are real values. Else, eigenvalues becomes imaginary. Now let's see what a diagonalization of a matrix is. So simple question is, not every matrix is diagonalizable. So before even talking about diagonalization, I'm just giving a statement, not every matrix is diagonalizable. Now let's see what a diagonalization of matrix is. Given a matrix A, first you do is compute the eigenvalues. How do you do that? Determinant of A minus lambda is equal to 0. So let's say you got two values of eigenvalues like lambda 1 is equal to 2 and lambda 2 is equal to 1. Now next is compute the eigenvectors corresponding to these two eigenvalues. Now let's say you got x1, so for lambda is equal to 2 you got two eigenvectors, 0 1 0 minus 1 0 1, and for lambda is equal to 1 you got an eigenvector 0 minus 1 1. Now you form a matrix S, which is simply the eigenvector matrix. So what are the three eigenvectors you got? You just fill in as columns. Now what is a lambda matrix? Lambda matrix is a diagonal matrix with only diagonal elements and everything else is 0. And the diagonal elements are your eigenvalues. So you have got S, you have got lambda matrix, S matrix, lambda matrix. Simply verify S lambda S inverse is equal to A. If it is A, then the matrix A is diagonalizable. So S lambda S inverse A is also equal to same. I mean, there is another representation of this, which is like S inverse A S is equal to lambda. S lambda S inverse is equal to A, and S inverse A S is equal to lambda. So simply mnemonic to remember this is IAS. I is inverse, A and S. So S inverse A and S is lambda. Now there is another deduction which says like A power K is equal to S lambda power K S inverse. Lambda power K is equal to S inverse A power K into S. Now let's see what orthogonally diagonalizable matrix is. So any real symmetric matrix is orthogonally diagonalizable. I'm just giving a statement. Now in the further weeks you see that every Hermitian matrix is unitarily diagonalizable. So symmetric matrix is for real world Rn. For complex world there is something called as Hermitian matrix for Cn, and these two are like same. And then for the real world we see what is called as a orthogonal matrix, and then for the complex world for Cn it is unitary matrix. Anyways, a real symmetric matrix is always diagonalizable. And before even diving into that, let's say what is a symmetric matrix. Symmetric matrix is A is equal to A transpose, right? The eigenvalues for these matrix are real, the eigenvectors are perpendicular. This is something that we need to remember. So is it possible, if it has distinct eigenvalues, then you say it is diagonalizable. Okay, this is the point I'm trying to tell you. When do you say that a matrix is diagonalizable? When there are two ways. You take that matrix and you simply find the eigenvalues and all are distinct. Then you say this is diagonalizable. Otherwise, don't even go for diagonalizing. Second way is you already know eigenvectors of all these things and they are independent or orthogonal. Then you say yes, this is diagonalizable. Then do all the procedures I have told you before. Now, orthogonal diagonalizable is whenever it is represented by Q. Like say Q is the orthogonal matrix. What is orthogonal matrix? Q transpose Q is equal to Q into Q transpose is equal to I. Simply is Q transpose is called Q inverse. A transpose, you're taking a matrix, you're transposing it and also inversing it, and both are equal. This is called as an orthogonal matrix. So what is the procedure for finding or letting know of like is it orthogonally diagonalizable or not? Simply take a matrix, find the eigenvalues, find the corresponding eigenvectors. Instead of finding, so you have written S, right? Matrix, set up a matrix S which is columns of the eigenvectors. Here instead of that you do columns of unit eigenvectors and simply perform this. A is equal to Q lambda Q transpose. If it is equal, then it is orthogonally diagonalizable. You can say that it is orthogonally diagonalizable, right? So A is equal to Q lambda Q transpose, similar to A is equal to S lambda S inverse, right? Or instead of Q transpose you can write Q inverse also, because Q transpose is equal to Q inverse in orthogonally diagonalizable. Now let's go to week 5. Week 5 we see Hermitian matrix. Hermitian matrix is a complex number matrix which is equivalent to that of a symmetric matrix for real matrix, but it represented as A conjugate transpose is equal to A. We know symmetric matrix is A transpose is equal to A, but A conjugate transpose A is equal to A is Hermitian matrix. So if given a matrix, do the conjugate of it, transpose it, and once you do that and it is equal to that of A, then you call that as a Hermitian matrix. For a Hermitian matrix, all the diagonal elements are real. So now here is a mnemonic. Real HD hero. So for a Hermitian matrix, the diagonal elements are always real. So diagonal entries are always real. Real HD is what this is, and hero is like for Hermitian, H stands for Hermitian, E stands for one's for eigenvector value and other for eigenvector. So R is for real, O is for orthogonal. So eigenvalues of Hermitian matrix are always real. Eigenvectors for Hermitian matrix are orthogonal. If the eigenvalues are distinct, the Hermitian matrix are orthogonally diagonalizable. similar to that of what you have seen. And all symmetric matrices are Hermitian. All symmetric matrices are Hermitian, definitely. And if you see the inner product, x transpose y or x is dot y in real world is here x conjugate transpose y and is equal to x1 conjugate y plus x2 conjugate y2 plus so on up to xn conjugate yn. And it is not cumulative. X dot y is equal to y dot x, but here x transpose x conjugate transpose y is not equal to y conjugate transpose x. Cumulative is not possible. And norm of x square is x transpose x. Norm of x square here is x conjugate transpose x. And some notable properties are x dot y is y dot x of whole conjugate. And in real world, a transpose whole transpose is a. Here a conjugate transpose whole conjugate transpose is a. And ab whole transpose is b transpose into a transpose. We know ab whole conjugate of transpose is b conjugate transpose into a conjugate transpose. Now equivalent of orthogonal matrix is unitary matrix. A unitary matrix is a complex square matrix whose columns and rows are orthonormal. So you have this mnemonic U is CM on. U is unitary, S stands for square, CM stands for complex matrix. Unitary is a square complex matrix. On is orthonormal columns. So unitary matrix is a complex square matrix whose columns and rows are orthonormal. Even rows. Wow. Now, so what is in real world is orthogonal, in a complex world it is unitary. So U conjugate transpose U is equal to U conjugate transpose is equal to I. That is U conjugate transpose is equal to U inverse. One simple example is cos theta minus sin theta, cos theta. If you see the rows or columns, they are orthonormal. Anyways, the properties of unitary matrix is first is CTU, then you have EU10. So CTU is like if U is a unitary matrix, conjugate transpose of it is also unitary. So U star, which is U conjugate transpose, is also unitary. So CTU is the mnemonic. A unitary matrix is always square matrix. A unitary matrix always has orthonormal columns. Eigenvalues of unitary matrix have absolute value equal to 1. That is, absolute value of lambda is equal to 1. That is EU10, right? So eigenvalue of unitary matrix is absolute value is equal to 1. And the eigenvectors corresponding to distinct eigenvalues of a unitary matrix are orthogonal. So 1, 0, it's not 0, it's O. EU1, O. Now every unitary matrix is not Hermitian matrix. Now similar to what you have seen, A is equal to Q lambda Q transpose. Here you see A is equal to U lambda U transpose, U conjugate transpose. So in real world you saw lambda is equal to Q transpose A Q, and in complex world you see lambda is equal to U conjugate transpose A U. Now this is called a spectral theorem. So here let's say A is equal to U lambda U conjugate transpose, right? So A is the Hermitian matrix and lambda is the diagonal matrix. Now there is something called as Schur's theorem, SCHUR, Schur's theorem, and here instead of lambda, if you replace it with upper triangle matrix, then A can be any square matrix. A is equal to U transpose U conjugate, A is equal to U times T times U transpose conjugate, U conjugate transpose, and T is your upper triangle matrix and A is any square matrix. Now quickly I'll let you know what the Gram-Schmidt's process is. Any basis vectors V1, V2, so on up to Vn, you put this in the Gram-Schmidt's process, this specific process, you convert them into orthogonal bases. So V1, V2, Vn, so on up to Vn, any basis has been converted to some U1, U2, so on up to Un, which are orthogonal bases. Now let's see what singular value decomposition is. So every m by n matrix can be factorized or decomposed into SVD form, single value decomposition. So A is equal to U, and this is actually a sigma. Let's also call it a sigma, but sigma in the symbol of E. Okay, so U sigma V transpose. A is equal to U sigma V transpose is simple the first starting point, where U is M by M orthogonal matrix, sigma is M by N diagonal matrix with non-negative entries, and V is N by N orthogonal matrix. Sigma 1, sigma 2 are your diagonal elements of the sigma matrix, which are nothing but square root of the eigenvalues. Now, what is the steps for finding the decomposed form, SVD form? Is given a matrix, first and foremost write down the formula. A is equal to U sigma V transpose. A transpose A is equal to V. At the end, so write V transpose, and the middle you write sigma transpose sigma. So A transpose A is V sigma V transpose. A transpose is equal to U sigma transpose U transpose, and A V is U sigma. Therefore, U sigma, you can write it as AV, and U is equal to AV times sigma inverse. Now first, these are the formulas that you know. Now what we'll do is, first we'll compute A transpose A and then find the eigenvalues of A transpose A. For corresponding eigenvalues of A transpose A, you'll find the eigenvectors, and once you find the eigenvectors of A transpose A, you do normal eigenvectors. So you'll find like not just the eigenvectors, but unit eigenvectors. Now after that eigenvectors set of a matrix with columns of unit eigenvectors is your V. Now once you get V, you already know A, and you have seen that from the formula U sigma is equal to A into V. So U is equal to A V sigma inverse. So you know V, you know A, and sigma is like simply diagonal matrix with square root of eigenvalues, and you do the inverse of it and multiply this and you get U, and you have successfully transformed the matrix A in form of U sigma V transpose. That is your SVD. Now let's see what week 6 is. Week 6 starts with stationary points. If f is a function, and if you derive it if you differentiate it 1 and equate it to 0, you get what is called as stationary points. And if you want to check if these stationary points are either maxima, minima, or form a saddle point or inconclusive. To do that, you have to do second differentiation. Let fxx, fyy, fxy be the second differential functions, and d of x comma y is fxx f into fyy minus fxy square. And if d of x comma y, what did you say? Yeah, d of x comma y is greater than 0 and fxx is less than 0, then it forms the maxima. When d of x comma y is greater than 0 and fxx is greater than 0, then it forms the minima. If d of x comma y is less than 0, then we call it as a saddle point. And if d of x comma y is equal to 0, then we say it is inconclusive. Now let's see. Let's find out if a given matrix is either positive definite, positive semi-definite, negative definite, or negative semi-definite, or altogether indefinite. Anyways, so indefinite is like if the eigenvalues, both the eigenvalues are positive and negative, then it is indefinite. So you can find it with two methods. One is eigenvalues method, another is vector method. So before even going there, I'll give you, if function f of xy is given ax square plus 2bxy plus cy square, again ax square plus 2bxy plus cy square, you can write this as in a matrix form of A is equal to A, B, B, C. Again, you got a matrix and you want to know if it is positive definite, positive semi-definite, negative definite, negative semi-definite, or indefinite. Simply use one of the two methods that I'm going to tell. Method 1 is eigenvalue method, where if all the eigenvalues are positive, then we call it as positive definite. If all of them are positive and at least one is 0, then we call it as positive semi-definite. If all the eigenvalues are negative, then we call it as negative definite. If all the eigenvalues are negative with at least one being 0, then it is negative semi-definite. As I told you before, all the eigenvalues, if they are both positive and negative, then it is indefinite. Now method 2 is the sub-determinant method. So if given matrix, you have to divide this into sub-determinants. So A1 is the single most left top corner determinant, then 2 by 2 matrix is yours A2, then 3 by 3 is your A3, and so on. Okay, now if all these determinants A1, A2, A3 are greater than 0, then we say it is positive definite. If it is greater than 0 and at least 1 being 0, then we have positive semi-definite. If it is alternatingly positive and negative, the determinants, then we say it as negative definite. And it is alternatingly positive, negative, and at least 1, 0, then we call it as negative semi-definite. Finally, we have, in the week 6, we have PCA, principal component analysis, and there are certain steps to follow. Now let's see, given data, x1 is equal to 0, 0, x2 is equal to 2, 2, x3 is equal to 4, x4 is equal to 4, 2. This is the given data. So first step is to find x bar. X bar is the average. Now once you find the x bar, use this formula, covariance matrix formula, that you need to remember, which is 1 by n sigma I running from 1 to n x minus x bar into x minus x bar transpose. Once you do that, you get a covariance matrix. Now for this covariance matrix, find the eigenvalues, and for the corresponding eigenvalues, find the eigenvectors. Now once you find the eigenvectors should be a unit eigenvector. Again, now once you get the eigenvector, now you simply find the projections. Projections is nothing but dot product of the data points x1, x2 with this before even that, so you got eigenvalues and eigenvectors. Choose the topmost eigenvalue and corresponding eigenvector. So this eigenvector, choose an eigenvector, is important, because the next step is finding the projections, which are alpha 1, alpha 2, alpha 3. Alpha 1, alpha 2, alpha 3 are your dot, let's say alpha 1 is a dot product of the first data point x1 and the chosen eigenvector. The chosen eigenvector is an unit eigenvector. So you get alpha 1, alpha 2, alpha 3. Third step is, again remember another formula, this third step is finding the new points, new data points, which is nothing but simply multiplication of the values you got alpha 1, alpha 2, alpha 3 with the chosen unit eigenvector. So x1 bar, xy bar is nothing but alpha j into uj, right? So you got new x11, x2 bar, x3 bar, and so on. Now finally use a formula called reconstruction error, j is equal to 1 by n, norm of xi minus xi cap whole square, or x bar xi minus x bar whole square, and you simply find the reconstruction error. Now variance is the chosen lambdas, all whatever you have chosen, you have chosen only one lambda, you add them up, and that is the variance of your data. Now this is the procedure for principal component analysis, but I'll quickly run down what this principal component analysis is and why it is used. It forms important part of feature selection. So you, for example, you start off with as many features as you can collect, but you find a good subset of these features. You may not depend on all the features for the computation efficiency and speed, and you find the good subset of these features, and this is therefore a dimensionality reduction concept of unsupervised learning, and you choose such subsets such that you are minimizing the construction error and maximizing the variance of data. So simply you are like projecting the given data onto a lower dimensional subspace. This is all about week 6. Now week 7 is week 7, 8 and 9 are part of optimization. So any machine learning problem needs some understanding of three pillars. One is linear algebra, probability, and optimization. Linear algebra provides for structural relationship between data. That is, if given data, you can clearly say, okay, these form a linear relationship. So that is what linear algebra is, right? You put a x-axis, y-axis, plot the data, and find what kind of relationship they have. Second is, let's say you draw a trend line, and all the points, you draw lines from the points to that line, and there is these lines are called, these distances or small points are called noise or uncertainty. So second pillar is a probability. Probability is a numerical estimate of this noise or uncertainty. But you have drawn a trend line, a rough line, but most of the times you need best fit line, right? So that forms the third pillar. From many infinite possible lines, you are trying to find the best fit line. That what needs is optimization. So linear algebra, probability and optimization are your three pillars. Furthermore, to best describe the optimization simply means best of something, which means least of something, which is least loss, or max of something, which is max reward. Okay, so for example, best classifier is something which is least loss or maximum reward. Now, if you see the general optimization framework, you can take a simple example of a rectangular form with leftmost bottom is starting at 0, 0 vector, and there is a grass at 40, 40, vector 40, 40, and the cow is at 20, 30, and it is tied to a rope of 10, and there is a fence at 25, 0. Now, general form of optimization has three parts. One is objective function, or four parts. One is objective function, two is the variable or parameter, three is the inequality constraint, four is the equality constraint. In this example, the distance, so the question is like how close cow can get to the grass. That is some important question. So what is the minimum distance of x, minimum of x, right? Let's say cow's position is x1, x2, and the distance of x1, y1, let's say x1, x2, okay, fine, x1, x2, and the distance of x1, x2, vector x1, x2, and 40, 40, if you see, is x1 minus 40 whole square plus y1 minus 40 whole square. I'm just neglecting the square root, and the minimum of this is what the question says. So objective function is always like minimum of x, min of x of function f of x. This is the objective function. Okay, and here in this case it is x1 minus 40 whole square plus x2 minus 40 whole square. How close cow can get to the grass. Now second is the parameter. X belongs to Rd, is a variable or parameter. In this case x is r square, x1, x2. Third is the constraints. Inequality constraint is one of the constraints. So gi of x is less than or equal to 0. In this case we have two constraints, inequality constraints. One is that it is tied to a rope of 10. So x1 minus 20 whole square plus y1 minus 30 whole square is less than or equal to 10 square. Other constraint, inequality constraint, is x, not, it is an equality constraint actually, which is equal to 25, right? Let's say h1 of x is equal to 25. So at x of 25 there is a fence. Now that is about general optimization framework. Now let's see an unconstrained optimization problem. So we are not talking, we're just leaving out the inequality constraint or the equality constraint. We're simply talking about minimizing x for a given function f of x. So for that, a machine to solve this, an iterative approach is needed, and we have an algorithm which does this iteratively and gives the minimum value of x for a given f of x. That algorithm is called as gradient descent algorithm. For a first order, this algorithm is something like this. Initialize at x0 is equal to r for t is equal to 1, 2, and so on. Then update xt plus 1 is equal to xt plus nu of t minus f dash of xt, where nu t is step size, which is 1 by t plus 1. Then end. This is your gradient descent algorithm for first order. For gradient descent algorithm for multivariate function, it simply says like initialize at x0 belongs to rd for t is equal to 1, 2, 3, so on. Update vector xt plus 1 is equal to vector xt plus nu t, which is a scalar, times minus grad of f of xt, which is a vector. Third, then end. So here negative gradient or minus f dash of x always points to a direction of decrease. Okay, and that being for a function, it is local minima. If the function is a convex function, then that local minima and global minima will be same. Now n of step size nt is 1 by t plus 1 is called as step size. Okay, and other than that, the representation of local minima in an equation is f of x cap is less than or equal to f of x if for epsilon greater than 0, for all x belongs to x cap minus epsilon comma x cap plus epsilon. That is local minima. For global minima, if you wanted to write in an equation, f of x star is less than or equal to f of x for all x. Then we have what is called as Taylor series, which gives global information from local information. What does that mean? F of x plus nu d. So d is the direction. Nu is, you know what, step size, right? F of x plus nu d is equal to f of x plus nu times of d into f dash of x plus nu square times d square by 2 f double dash of x, so on. So if you know simply x, you can find x plus dx and nu d, which is global information. Now let's simply look at w as a vector w1 w2. Okay, and d is any direction, and let's say you are picking a direction which is perpendicular to this, so d transpose w is equal to 0. How does this look like? Simply imagine a vector w which is like a 45-degree angle, and draw a line perpendicular to it, and you call it as d transpose w equal to 0. Now imagine d transpose w greater than 0. You can just shade off all the region to the right side of this perpendicular line. D transpose w is equal to 0, and d transpose w is less than 0. You can shade all the region below this perpendicular line. Now how do you represent? Replace w with del f, right? Del f. So that is the vector, and minus del f would be the exact opposite. So if del x is represented that way, minus del fx will be your opposite way. So that is simple representation.